So thank you, Alon, for hosting this special seminar. My name is Amir Tigani, from Civil Environmental Roboticist. I had the graduate program of the Technical Autonomous Systems and Robotics program. And this is a joint seminar series between the TASP and Mechanical Engineering. And I'm about to present Howie, which I've known for 20 plus years. He was my first advisor, second advisor as well, for master's PhD. Howie's been working on robotics for many years, and I think one of the special parts is how his work is fundamental on one hand, and also applied. And you see, he'll talk about a few spin-offs. Will you mention spin-offs?
First thing.
6 spin-offs, most of them successful at one point or another. Many patents, many awards, and so on. We don't have time to discuss all of them, but Howie will try to kind of give a glimpse of the journey throughout the years.
So, I thank you.
Yep.
Okay, so my name is Howie Choset, and let's see, is that gonna work? I hope it was working.
Let's do another click.
Yeah.
String. Again. I know. Where is it?
It's working before.
Yeah.
Oh, there we go. Right, perfect. All right, let's put in that video. All right. Yeah. Oh, I can go back. Yeah. Okay, so let me tell you the real reason why I'm here. Okay. So yes, I do want to talk about snake robots, and I spent a lot of time working on them. But really, I just want to impress a bunch of smart people. Okay, let's just start there. And what's not listed here in this list of agenda, is I was afraid Amir or Alon was going to see it, is every so often I can tell an embarrassing story about Amir when he was a student or Alon when he was my postdoc. You know, I think it's important you should know the origin stories of where they came from. I also want to, steal your ideas, okay? And I want to rejoin the Jewish mafia, okay? And I had a nice, inroads into technology a while ago, and I want to bring that back because it's been nothing but great for me, and I hope somewhat good for them. In terms of Amir, I don't know, what's the embarrassing story? As he said, I was his master's thesis advisor, and then I was co-advisor with him with Matt Mason. I don't know if you've heard of Professor Mason. And eventually, Amir had to tell us we can't meet the three of us together, because when the three of us got together, Amir was the responsible adult, and Matt and I were just joking around the whole time. Amir got a little frustrated, never showed it, and then we had separate meetings after that. I think what I'll do is I'm going to tell my story a little bit in reverse. So normally professors, we do basic research. Sometimes we do applied research, deploy systems, and so forth. What I want to do is go backwards and then go forwards. So one thing I do want to ask is, I thank you all for coming here, but for you young men, please put your phone away. Thank you. So because I know it's selfish of me to have all of you look at me for every time, but what the hell? Again, I want to impress smart people, every smart person here. So let's look at his companies. Med Robotics, okay? This was the first company. Alon was the co-founder, Marco Zanatti. So the Alon story. So the way I met Alon is I was at a Seder in Pittsburgh. I was invited, not because I was the plus one. I was the dates, and I wasn't the person they wanted there. And I was sitting across the table from this guy who asked me, "Can you find a job for my friend?" And I said, sure, why not? The guy, he drove a PT Cruiser. I don't like PT Cruisers, so I'm shocked I helped him. But so I met Alon on the phone. We talked, and I couldn't find a job for him. And then Alon said, well, you seem like a nice enough person. Can I work with you? And I said, okay, seems like a reasonable thing. He's a bright guy. And then he said, but I can't start for another year. And I then at the time thought, that's fine. And I didn't know at the time that you can't give a job offer over a year in advance or a year in advance. But it's one of the best things I ever did in my career. And I'm glad he came a year later. But it was just another serendipity, random thing that brought us together. Without Alon, all the medical robotics work that my group does just wouldn't be, simply put. outside of my students getting their PhDs, which is Amir, the proudest experience I had as a professor was when my robot operated on a person for the first time, and that wouldn't have been without Allah. We thought, I started a second company called Heavy Robotics with my students, and this was a scam. It was a trick. You see, these guys, what they do is they graduate and then leave. Okay. So my thought was, why don't I keep them nearby by starting a company with them, divide the equity in equal parts, and off we go. And they thought that was a good idea. And really, I'm still basing my research and education on what they tell me what to do. This company, Heavy Robotics, makes these modules. It's called Heavy. It's a Japanese word for snake. We thought we'd be making modular snake robots, but really all kinds. I figured Bito Robotics, this is a company that's now based in Shanghai doing multi-agent systems. And then most recently, I just started this other company called Pipe Force, where we go and map the inside of pipes. Let's see if that'll make the video go. So here, the hero of this story is not the robots. You'll see a robot, who cares? It's the mapping sensor. You'll see a little ring sensor. Being able to get sensor readings from confined spaces is one of the things my group is among the best in the world to do. And building these high resolution digital twins of these pipes provides information data, not only the municipalities, the cities need, but if you're a construction firm wanting to build a new project. You see, I don't know how it is in Israel, but in the United States, we don't know where our pipes are. Okay. In fact, anyone have a guess as to how often a pipe fails in the United States? Underground pipe? Every day? So it's one a day? Every minute? It's one a minute. So in the time we've had this talk, think of all the pipes that have failed. So we're trying to fix that. I also started this manufacturing institute. This is one of President Obama's manufacturing institutes. And the idea here was to bring manufacturing back to the United States, blah, blah, blah. I think that's stupid. What we want to do as Americans, at least, is be the innovators of the next generation of manufacturing. Let our peers in Asia and Europe have what they do. And this is something else. It doesn't matter. The only thing is these two companies, this is the one I started with Mellon, they're out of business. So they're not all success stories. Actually, I take it back. Success is what you define it to be, okay? But certainly still being in business is one measure of success. So here's one of the robots we recently built. It's an underwater snake robot. The video is a little choppy. I'm not sure why. It took us about 6 months to build this robot. Okay, even though it's one of the, it's a pretty advanced underwater maneuverable robot. Anyone know why we did it so quickly? Any guesses? There's 2 reasons. No investors. I'm sorry? Nope. There's 2 reasons why we were able to build this robot so fast. Nope. The first reason is we embraced modularity. So Heavy Robotics is that modular robot. We got very good at building modular systems. So maybe I lied. We didn't build it in 6 months. We built it in 20 years. It just took us 19 and a half years to build the modules, half a year to build the robot. The other reason why is I've been very fortunate, as these 2 gentlemen can attest, to have been endowed with wonderful students and staff and faculty collaborators, to be able to do this kind of work. One fun thing we're doing is this project actually just got canceled. It's not a Trump cancellation, just so you know, but it was canceled. Saturn's a planet. There's a moon called Enceladus, and this moon has the largest known ocean in the solar system. And what they wanted to do is go into the South Pole. This is JPL. This is where I used to go to graduate school at Caltech, and Caltech runs JPL. They want to build a snake robot that goes underneath. Is in the South Pole. There are these geysers, and it's only 2 kilometers thick. A robot goes inside and swims in the largest ocean. They were saying there'd be life there. There's no life there. We know that. But you all know me well enough to know if someone says, "Hey, do you want to build a snake robot to go to a moon of Saturn?" The answer is an obvious yes. In fact, I think all of you would agree, would do that too. However, there is other working space that we're now doing. Okay, so space is no longer the side education or entertainment for wealthy nations. It's actually a new business in space. So right now, anyone have a guess as to how many satellites are circling the Earth? 8,000. When I started this project with 6,200, 8,000. How many of them work? Half. Yeah, half, not five. It's only five. How the hell are we talking right now? So it's half. And the reason why is these satellites were designed to only work once. Once they run out of fuel, once they live their lifespan, they're done. It wasn't that they were bad. Some of them are bad. So what we want to do is be able to refill the gas tank, so to speak. Really, what we're doing is we're putting a mission extension pod into the back of an existing satellite. It has a new tank of gas, a new navigation system, and then voila, you're back in business. Think of the trillions of dollars that are floating around in space, and all we have to do is solve a simple peg in hole problem. All right. The only thing is, it's a little bit different from a peg and hole problem. Remember, you're in space, so you're floating around. Okay, it's a little more complicated, but still, it's not. I want to say it's not rocket science, but it really isn't. But the real trick really is managing contact. How to do planning with contact in space. And what we did for that is we built this system. We call it a holodeck, because So here are these UR5s. They're on a rail. Here's the tailpipe of the satellite. Here's the peg for the mission extension pod. And what we're doing is we're emulating being in space. So if you go up to this, actually, I'll play this video. Let's see if it'll work. If you go up to the tail and give it a push, it'll float away as if it's in space because we can't emulate lack of gravity in my lab. And you really can't do anywhere. Up until this point, their plan was make it work in simulation and then launch into space and hope for the best. Okay. Here, not only can we simulate being in space, we can also simulate being underwater, or if you like being in honey, we can do that too. But what's cool is now we can program these robots, understand the contact mechanics, and simulate it in a gravity-free environment. Real data, not simulated data. So this is another sensor we built. We're very good at building embedded sensors, and here it is scanning things in. We built this for Boeing for manufacturing in confined spaces. And then another robot. These are these force sensors that we've gotten very good at building. And this is a needle insertion, ultrasound-driven needle insertion robot. And really, this needle insertion and closing the loop on force, it's nice. This ultrasound probe, it's processing the ultrasound data. That's the star of the show. It's closing the loop. The robot really isn't that big a deal. Actually, even closing the loop, the algorithm or the machine learning we used is not a big deal either. It's generating the synthetic data. And we've gotten into putting our sensors into 3D printing machines to regulate 3D printing of materials, but also repairing devices out in the street, out in the wild. And then we do a little bit of this car painting. I did this work with a deaf, were you there for this? Yeah, the deaf Jewish Cuban refugee was our point of contact at Ford. And recently we started doing airplane painting, really inkjetting with Boeing with a regular white Christian American. But it's still a good project. And I think I'm very fortunate to have these people work with me in developing these nice systems. But the reason why you talk with us among faculty isn't to build new systems. That's what industrial engineering or project engineering people do. You come to us when there are scientific problems that have to be solved in order to build these systems. So really, as a professor, these are some of the ideas that we think about in my research group, how to make problems simple, okay, either through dimension reduction, interleaving search, and so forth. The thing is, lately, some of you may be aware of the recent craze in AI. Okay, for those of you who are old enough to know AI in the 80s was a bad word, now it's the word we all take. The thing is, to me, I'm still afraid. Okay, it's like a black box to me, all right? Here I am developing these algorithms that do all these wonderful things with intuition and such, and then some kid in the basement of his parents in the Netherlands uses a machine learning algorithm and outperforms what we do, okay? And I'm still confused about that. So you're all getting me going through this existential crisis of where research is going to go. I really hope that, I don't really believe machine learning algorithms are going to make humanoid robots, create an army and beat the good guys. Because, well, for one thing, the war better be over in 30 minutes because the power runs out then. I just think that robots are such a difficult problem to play with that we still need the fundamentals. All right, so let's talk about some topics. So the first is snake robots. So one of the challenges with the snake robots is how do you coordinate all those degrees of freedom, all those joints, to get this purposeful motion? And what we've done is we've taken recourse to this area called geometric mechanics. And in a sense, this is my friend Jim Ostrowski. He's an agricultural robotics guy now. We'll look at a system, instead of the configuration space, instead of all joint angles, we'll call it, we'll separate our configuration space into where you're located and what your shape is. So I'm in the same position, different shapes. All right. So when a horse, again, the video is a little weird, gallops, okay, it's having a cycle in its shape space to cause a displacement in its position space, okay? And that cycle is called a gait. Now, you don't have to, you can have lots of animals that don't have legs implement gaits. This is a snake robot, by the way. It's climbing up a channel. And what we're going to do is develop this, use this idea to generate gaits for systems that are elongated. So like any good engineer or young scientist, you start with Lagrange's equations. You make some assumptions. These two assumptions, this one is sort of conservation of energy, conservation of momentum. If you think about it, how can you not conserve energy? But still, conservation of momentum. This one here is pretty much saying, if I'm facing this way, that's left. If I'm facing this way, that's left. So it's like everything relative to me. So this is a symmetry of Lagrangians. This is non-holonomic constraints being symmetric. After you make these assumptions, you end up with this single order system where this is your body velocity and this is your shape velocity. These are your joint velocities, and this is how fast you're going to move. And that matrix in the middle, what does it look like? To the roboticists here?
Jacobian.
Thank you. He who has seen this talk before. We call it a connection. It's a little bit different from a Jacobian, just a little bit. However, our contribution to this work of geometric mechanics, people have been thinking about it, including Nobel laureates. Ours was, and now the roboticists are going to go, really? That's it? Was applying what we know about the Jacobian to geometric mechanics. That's it. So let's look at this Jacobian geometric mechanics. What I did here is I plotted a row of that Jacobian for this robot here. Its position is X, Y, theta, and its joint angles are alpha 1, alpha 2. So for its Jacobian, its connection, I plotted the first row. It's a vector field. Each row corresponds to a vector, and each vector in this vector field is for a different shape. So if I'm at this configuration and I excite my joint angles in this direction, I'll get maximal X displacement. If I'm at this configuration and I excite my joint angles this way, I'll get zero displacement because, the dot product of vectors, orthogonal vectors, is zero. So what you got to do is just draw a loop in this vector field and off you go. All right? That's hard. So what we did is we took recourse to Stokes' theorem. Stokes' theorem, you take the path integral inside is the curl, okay? You have the curl now, and you have this beautiful height function where if you draw a loop now, you get the same thing. You can just look at the volume contained in the loop, and that tells you how much you'll displace. So here, if you have this valley over here, you get a lot of negative displacement. This is no displacement because it's on the left and the right are the same. These white lines are zero. This is all positive, all negative. You want to draw loops around big positive bumps or big negative bumps. Voila, you're designing gates. So this picture here, it's a little faded. I can't blame your computer for this. This is my fault. The vector field here, the height functions on top, and you see we're drawing a loop. In the X direction, we get that volume that displaces us in the X direction. Easy peasy. So you're probably thinking, what about the snake robots? Okay, so here's where dimension reduction first comes in. If you think of that 3-link robot where alpha 1, alpha 2 are joint angles, instead plot the curvature of that robot, and at the joint angles, you have a Dirac delta for the joint angle. So instead of doing the Dirac delta, what we'll do instead is we'll have these beautiful sine and cosine functions of curvature. So we're no longer looking at joint angles, we're looking at coefficients in front of modes. And by doing the inverse kinematics, so to speak, or determining what the loop is in our shape space of those coefficients for the modes, we can get this robot to move forward. And this is a curve called the Serpenoid curve, which Professor Hirose intuited back in 1971. We were able to show by combining something that Greg Tricchian did in our work that this is what you get. So here's the vector field. Here's that height function again. It's a contour plot instead. And these are just different values, different size loops that get bigger and bigger. You can see there's a maximum and how well we do. So here's an example of where we used our robot. And this is Mexico City. It's about 6 or 7 years ago. And it was an earthquake. And there's this action shot here. Over here is Julian, my student. Over here is a young gentleman who thinks his sister, she was in this building. And we're trying to crawl through looking for survivors. You can see here, we really weren't well prepared for this. Like that bucket there, that's our sun shield. But it was still, it's an example of where we can use these robots. We also were challenged by, it wasn't a flat ground. It was sort of a bumpy ground. Even though we assumed we're in flat ground for our gait analysis, it wasn't. And that's because we're programming our snake robot, our supposedly bio-inspired robot, as if it's an industrial robot. So what we do instead is we built these new actuators. They're called series elastic actuators. So you have a motor, there's a spring, and there's the output. If there's no load, everyone spins together. If there is some load, there's a torsional deflection. And from that, you can compute how much torque is on that joint. You can close the loop for force. So now we have a way of delivering force or closing and sensing force with our actuators. So what we did is we wrote out this impedance controller. And again, we used our gate equations to get from 16 joints down to 2 joints. And we literally just run our gate controller, our impedance controller on this gate space. We put the robot on this pile of rocks. It is told, go move on this flat ground, and the impedance controller does the right thing to overcome these obstacles. Of course, there's a certain size where this won't work anymore. So this is just a controls problem. Once you have to go to a higher size, it becomes a planning problem that I'm not ready to think about. That's one of the reasons why I'm here, to find collaborators. So let's see. There's a funny cycle we're going to make here in terms of manufacturing. So remember I told you about that manufacturing institute. If you look at this manufacturing facility, do you see the cage for the robots? Where is it? No, the cage is for the people. The people and the robots are isolated. This is what manufacturing is today. What's funny is if you look at a robot in the 80s, okay, and you look at a computer in the 80s, so I guess Mellon, Dr. Degani, you remember these computers. Those are floppy drives, okay? Now, in the 90s, computers got a little bit better. Robots stayed the same. And computers are even getting better. By the way, the founder of this company was my student, Matt Rogers. This is Nest. If you remember, his company was purchased for $3.2 billion. By the way, we would have been impressed if it was 3.2 million, but 3.2 billion, okay. But look, the industrial robot looks the same. We really haven't changed our robots for industrial robots. So one of the things we want to do is make these modular force-feeling robots do other assembly tasks that conventional robots can't. They can't because they have to get very precise, because if they're off by a little bit, boom, something breaks. Now, if you have compliance control, you don't need as much position control. Here we're showing one of our engineers building a robot arm in 24 minutes. So one of the things I'm trying to push is this notion of mass production in quantities of one. And if you can customize your automation almost every day, you can customize that product. So there he is. And it's funny, look at all the different robots we're able to build with these modular robots. But here you can see he's teaching how to plug something in. Here we're assembling screws. What makes this a success is that he can feel the force in. This is Julian again. This is sort of as a joke. So exoskeletons are not a joke. Let's be clear there, okay? But he built this backpack robot, which gives him a third arm, which also people both in the auto and airplane industry wanted because they want to be able to hold something up while they're doing their thing. So the thing is, it's kind of a funny question. Given a task, how do you figure out what robot to build? Okay. So here's one little thing I'm going to confess. When we talk about something that's geometric in basis, I go into a little bit of detail. When it's machine learning, I just show one slide. Okay. Because again, I don't know why. But what Julian came up with was this network. It's a discriminator generator network. And that you pretty much give the robot a task. Let's say navigate over some terrain. And you have, I don't know, God gave you some latent prior or your friend gave it to you, who knows? It goes into a generator and it just generates a bunch of designs. We then evolve those designs using whatever evolution network you want. That's not a big deal. And then you have this discriminator over here trying to figure out, was this an original design or an evolved design? Now, some of you who have machine learning background know this network from the vision community. They want to ask, is this a synthetic image or a real image? It's the exact same network, except is it a generated or evolved image? And then you build this discriminator, and now you have an arms race. Can the generator build something that you can't tell it's evolved? And when the discriminator finally says, I can't tell, you stop. Okay, and that's how we generate our different modules right now. And that's the best we can do. Okay, I hope we can do better. This reward net is a detail I don't want to get into right now. So here I am. I did some robot archaeology. So here are my friends. That's me over there with the Pittsburgh shirt, wearing ladies' glasses. I didn't know it would be that windy. And we were doing some archaeological work off the coast of the Red Sea and underneath the pyramids. Here's my snake robot. It's kind of mangled. The robot was confiscated. This is about 12 years ago. It was confiscated by the Egyptian military. After 4 days of negotiation, there was a bribe. Okay. Think about in the back of your head what the bribe. Don't shout it out now. I know you know the answer. And then after, I'll ask. I'm curious what you think the bribe was. And here's me. These are ancient Egyptian ships, and there's me with my Pittsburgh shirt. But we were challenged by going up sandy terrain. We couldn't do the sand. So at the same time, this friend of mine, Dan Goldman, was studying these lizards called sandfish. And these guys, these sandfish, they kind of like tuck their legs in and go quickly in the sand. And he built a robot. I just named it Danbot after Dan Goldman in these little yellow BBs. And it's a 3-link robot, again, like you saw before. And what he tried to do is simulate how to make the robot, his 3-link robot, work in these BBs. So Ross Hatton, my student, noticed this and called up Dan, and he said, hey, we have an idea for you. We have all this geometric mechanics that we can use. So what we did is we put the robot at every possible configuration and then tweaked at little velocities, noted them, and for some reason, the universe was kind to us. And the relationship between the input shape velocity and the displacement body velocity was linear, just like the connection, just like the Jacobian. Okay, I don't know why that's possible, but that's what happened. Okay, so we created a height function again, and we're able to draw these gates that just work instantly. There's no way a human could intuit to make a gate in a granular fluid to rotate in place. No machine learning algorithm will produce this, okay, without the knowledge of the geometric mechanics. And this is something obviously we're very proud of because it was the fundamentals that got us to do some capability. Where we're at now is I think a lot of you have seen this dead fish experiment. So George Lauder killed a fish and then put it in water really quickly and then bombarded it with vortices. And then that excited the natural mechanics of the fish to want to swim upstream. And one of the things I believe, and this is just that, and I'm not saying this because I'm trying to take credit, okay? I'm taking this because I don't want you to think it's common knowledge, okay? Is that when little fishies are swimming in swarms, one means of communication in addition to the vision are deploying vortices at each other in order to locomote forward. And it looks like there's evidence that that's true. What we did is we put this 3-link robot on a moving plate. And my student, Tony Deere, he, with Scott Kelly from grad school, we were able to develop gates that either we shake the plate and the 3-link robot moves, or the opposite, You put the 3-link robot on the plate, and it makes the plate move. And that was Tony's thesis. And now I have another student who wants to be able to take this 3-link robot and cause the other robot to move. For those of you who know about mechanics, what we're encroaching on is the experiment where if you put a bunch of metronomes on a movable plate, eventually they'll all synchronize. Yeah, we rediscovered that. But we really haven't got much forward in this. So I'm really hoping to figure this stuff out soon because the funding runs out next year. All right, let me talk about medical snake robots. I'm going to change subjects. So one of the things I want to be able to do is democratize medical care. I want non-surgeons to deliver surgery level care. I want technicians to be able to do what doctors used to be able to do. So more care can be received anywhere by anyone. This is one of my personal things. And this is something that a philosophy I started with a long time ago. So this is the surgical snake robot. I'm sure you all know the benefits of minimally invasive surgery. And this is the actual proud moment. This is from our first in human procedure where the snake robot is going around a 75-kilogram woman's heart. This is the direct visualization. So here's the beating heart, and you see her lungs up there. Your lungs are white if you don't smoke. And there we are. That's nice. The thing that's pretty impressive is this woman went home the next day, and this procedure was done without a surgeon. Okay. I'm making it seem like it was a swimming success, this first in human procedure. I'll let you know. You all know the company failed, so I guess that's no surprise. I really believe that we were going to walk out of this. I see I'm struggling not to call it an experiment because that made them mad. This operation, and then companies were going to buy us out. Alon and I would have been like multimillionaires, and you all would be extra nice to us. But that's not what happened. But we did have a successful first in human procedure, and the company lasted for 10 more years. But where we are now is this robot did clear the FDA. It's the first surgical robot to clear the American FDA with the word robot in its indication. Okay, so in the eyes of the United States government, Alon and I invented the first medical robot, if you want to believe that. This is cool. This guy in Australia removed a 6-centimeter tumor out of someone's neck. So no broken jaw, no radiation. The guy went home and had spicy food the next day. This is what I want to work on, natural orifice surgery. So this is, again, one of my, I guess, white whales. This is something I want to do. The idea is you go in through the mouth or up the butt, or in a woman's case, and other organ orifices. You poke a hole in the luminal space, and you go perform the procedure from there. Now, a lot of you are thinking, that's not good, but your luminal space is meant to heal. Certainly much better than your flesh, bone, and muscle. So the procedure I was always interested in was going after the head of the pancreas for pancreatectomy. Because if you have pancreatic cancer, or if they suspect you have pancreatic cancer, you're in a lot of trouble. Here, I know some of you didn't think you'd see a snake robot shoved up a pig's ass today. What's even better? 2. So here we are operating on this pig. We needed one to see, the other to do, and we're removing the pig's the tail of the pancreas, not the head. And this is something that's really been on hold for many years because I just haven't been able to convince sponsors to do this kind of work. But I have a good feeling that's going to change soon. But this is another kind of future work I'm looking to do. So let me change subjects and talk about this ultrasound. Here's this needle guided. So nobody likes looking at ultrasound, right? The only time you're happy to see ultrasound is if it's a baby and the baby is yours. Okay? After that, no. The benefit of ultrasound, however, is it's portable. It's not that expensive. It also has it's non-lethal. The thing is, it's noisy, difficult to interpret. There's a lot of problems with ultrasound. Okay? What we did is we developed this algorithm, which I don't think is such a big deal. This is where's Dan? I think this is around the time when you were here at CMU. We developed this algorithm called URAFT, and it's able to do an impressive amount of vessel deformation. Okay, actually, the algorithm, again, not that impressive. What is impressive is that we generated the synthetic data I really want you all to pay attention to me. So can you, Jeff? Yeah, please. I came really far today. Okay. I had to go on 2 trains. All right. Uh, and likewise, when you come visit me, and I hope you do, I'll show you the same courtesy. But what really made this work impressive is we don't have labeled ultrasound data. It just doesn't exist. So what we were able to do is develop an algorithm to synthesize ultrasound data. And this algorithm, that's what we're calling URAFT, is based on this non-deformable registration technique that I'm going to show you right now. So here we're able to predict how vessels will decompose. Here we can predict what the heart rate of the pig is. Here we're doing some. So where's the needle insertion? There's needle insertion in here and whatever. And what we've been able to do is actually insert a line into a femoral vein of a pig. This is an art student. He did it on his first try because our algorithm was so good at aiming. The robot was able to get the needle in, and then he could thread a line after that needle. So how does this work? We have this approach called URAFT. RAFT is a deformation, a deformable registration approach, but requires a lot of data. What we did is we kind of doubled URAFT. So just like with the surgical snake robot, I took Bob Sturges' idea and doubled it. That's what I did here too. So you start with a reference image and you deform it. So you press it, and we'll press it at 10 known forces. Okay. And then we use RAFT to figure out, what the deformation is. And this is again in training phase. We then have this other network that will undeform this image. So this image here is a reconstruction of this deformed image, but it's reconstructed, hopefully looking like that guy. We then take this reference image, we put it over here, and we're going to do the same thing again. And when we're done, we're going to have a reconstructed reference image that should be the same as the original reference image. So now we no longer have to label our images. We just have to force this image to look like that image. All right, so that's what we call URAFT. So it's this unsupervised RAFT. And there's different loss functions you can use. I don't know which ones. My student likes this one the best. And with this, we then can synthesize all the data we need in order to run these algorithms. What's scary about this, and this is what's freaky, we go 2, 4, 6, 8, maybe 10 newtons at different deformations for the training. We can interpolate to 0.1 newtons. That's fine. But we can extrapolate also. In fact, this thing can go and predict when vessels collapse, which is weird. There was a big ventilator craze. I think in the interest of time, I'm going to skip over the ventilator work and talk about, I have like at least 3 or 4 more topics, but only time for one more. So I'm going to talk about this multi-agent search work. The application that motivates this again is a search and rescue application. And, if there's a big disaster, what you want to do is figure out where can there be signs of life. And we, the roboticists, the computer scientists, engineers, obviously we're going to send the robots out to go look for the signs of life. The question is, with our limited resources, where can we send the agents? So let's say we have some understanding as to where things are. So we think there's a lot of victims here and a lot of victims here. We can exploit that knowledge, but we may get stuck in a local minimum. All right. The other idea is we can just explore, constantly look around, but maybe we won't be exploiting the information that we have. What we want to do is to balance both of them. And here, this is the so-called ergodic search. We're going to develop algorithms where the trajectory spends a proportionate amount of time in a region that's it's in proportion to the belief that there are victims present. So if there are a lot of victims here, we'll spend more time here, but we still spend some other time going in between. So let me explain what this ergodic search is. This picture here, there are 2 distributions being visualized. The obvious one is the information map, where gold means lots of victims, blue means very few victims. And the other distribution is this purple line. So it looks like a line, but really think of it as a distribution that has a big ridge. Okay, so it's a ridgy thing, and the ridge, the top of the mountain, follows where the robot is. And by controlling where the robot goes, you change where that distribution is. What we want to do is force the difference of those distributions to zero. So the way we'll do that is let's plot these two distributions in a Fourier domain. This is a two-dimensional for visualization purposes. The Fourier domain has more dimensions. And these are the coefficients of the trajectory of how the robot moves. These are the coefficients of the map. And naturally, what we want to do is force the difference of these coefficients to go to zero. And in doing so, we'll get this proportionate time spent property. And this number here at this moment is called ergodicity. So by forcing the ergodicity to go to zero, we can get this feature. Here, what you saw was as this dot went from here to here, you saw the ergodicity being plotted. The reason why there's this up and down is that that's a little bit of a look ahead. Notice if you don't look ahead at all, you're going to stay put. You need some future information. So that's nice, but what if you have, I don't know, what is it, many one robot and many you have many agents in one map. Okay, so if you have lots of agents in one map, you can understand how here you'd be going back and forth with one agent, but with two agents, you can now minimize your ergodicity and naturally go to those maxima. So I think the real problem is the other way around. When you have one agent and many maps. So let's do one agent and two maps. The way that works is, so an example can be is, again, we're looking for survivors, but let's say there's a gas leak and you want to, find the survivors, but you want to make sure nothing's going to explode. And this becomes a multi-objective type of search problem. And where's Oren? Is it Oren? Yeah, this is where the subtle mistake is. Yeah. So again, if we put these two maps into their Fourier spaces as such, if we go to this map, yes, the ergodicity goes to zero. Hooray, that's great. But there is this non-zero ergodicity associated with the gas leak, and that could be bad. So the other option is, why don't we go to this guy here, but then we won't find the survivors. So the compromise, you might think, is go to, the dots are, there we go, go to something in the middle. Okay? And that's maybe not a bad choice, all right? But what happens when you have multiple maps, when you have lots and lots of maps? Here it's just two maps. Here, at the very least, what we've done is we've minimized both the sum of the ergodicities, the sum of the squares of the ergodicities, and the one we really care about is we've minimized the maximum ergodicity. Okay, that's what we've done by picking this thing in the middle. We weren't just trying to make a fair compromise. So, and of course, with these two, if you go to this map here, so it's a scalar multiple combination of those two maps. This is a detail I skipped. Here's a map, here's a map. We create a virtual map that's the combination of those two maps, or it's the center of the circle of those two maps. These are the paths that you get, okay? It's the same path, on two different maps, but it minimizes the maximum ergodicity. So now it gets more interesting. What happens when you have, say, 3 robots, 5 maps? Okay, a game you want to play, in this example, it seems pretty straightforward. You go to the center of this circle, center of that circle, and then this guy gets its own map. Okay, this minimizes the maximum ergodicity. All right, but what we want to do, I can't go back, can I? What we're really going to do is we're going to, when you have K robots and M maps, you only have the opportunity to cluster K of these M maps. So the optimization that you perform is cluster these K maps so that the circle enclosing the different maps has the smallest maximum radius. Okay, and that's a straightforward, when I say it's a straightforward optimization problem, of course, it's an optimization problem that grows in whatever complexity, but that's something we know how to pose. So this is our way of doing team assignment. Right? How do you associate one with another? So I guess the other issue is, what about heterogeneous agents? When your agents have different sensor properties. What we did there is we recognized that in this spectral coefficients, for the higher order terms, it's like a sensor that's really nearby, narrow sensor, and the lower order terms are a big fat sensor, lower resolution. And when you make that recognition and optimize for that, you automatically get this allocation scheme that tells you, fly over big distances to mitigate it, ergodicity versus this other little term here. And again, there's some machine learning thing that figures out what that allocation should be. So I am going to stop here. I didn't get it. I do have one more topic, but you guys have to go away at 15:30, and I want to stop and take time for questions. So I'll skip over all this stuff and have a closing side. This is the traveling sales. Oh, we're doing moving agent traveling salesman problems, which are fun to do. But we don't have the time for that right now. Here you're seeing the cities are moving and the agent has to find a path to go through those cities while they're moving. And we did that in 3D, and then we do it for different kinds of robots with curvature constraints. This is close enough. You have to get near the city, and this is with robot arms. And I'll skip all this, how we do it, and there. I'll just leave this video. I'll leave this thing here. All right. Well, again, my lab has a lot of projects. As Amir said, we do run the pipeline from basic to applied research. I like to think that the applied research drives the basic research. And there have been these themes in the work from from these confined spaces to biological inspiration and so forth. And these are the deeper ideas that I think we're pushing. I just don't see how to put them all together with that black box yet. And that's me. All right, thank you for your attention, and I'll take some questions.
We spoke earlier about the modular snake robots and reducing the dimensionality by defining gates. Does that only apply to, is that only limited by configuration spaces that are manifold or that are not continuous? Because I saw like a sort of configuration space curve, and it's.
So I don't think that's. It's so rude of me to say it this way. I don't think that's the right question. Okay. I thought you were going to ask, is it limited to systems that have a cycle, a gate?
Oh, I actually have another question. Similar.
Okay.
I was thinking, do we limit ourselves also? I think, why is a car or a helicopter or maybe like a plane? Why can a plane fly faster than something natural, or a car drive faster than something than a cheetah? And it's because it's not confined to like sort of a gate paradigm.
Well, that's a different thing. Okay, so so there's three questions.
Yeah.
Your two and mine. So first, the framework is prescribed only for gates, anything with cyclic motion, but yet there's these non-gate motions. And we've played games to do that, but essentially we'll just say integrate the connection vector field, don't use Stokes' theorem. Maybe I could backpedal from there. For the configuration spaces now, what if your shape space is a torus? I think is what you're asking. So the question is that what we've been able to do is in our current work, you have a loop. There's an inside and an outside. So in the inside, you do the path integral, you Stokes' theorem, and voila, you have what's on the inside as your volume, off you go. But if you have a loop around the torus, where the loop is, where the winding number is not zero, say it's one, you don't have the inside and outside that you enjoyed a moment ago. So we actually have two approaches for that, and I'm not sure which one's better, but the one that's easier for me to explain is, let's see. You draw a loop this way, and you sort of move over, and you draw another loop back. Okay, so in a sense, you're unfolding the torus. Okay, so you have your torus, we'll unfold it, we'll make it into a square. So I have a square now, where this side is identified with this side and this side is identified with this side, okay? And then let's just take a diagonal line. That diagonal line corresponds to the loop we were just talking about, okay? So you have your diagonal line, where the hell's the gate? So what we do is we insert a line this way and a line that way. Okay, we just insert it, okay? So now we have our area again. Hooray, we're happy, okay? But you're like, what the hell? You just inserted this line out of nowhere. You're not allowed to do that. So what we do for that is in advance, we pre-compute what this line is and what this line is using the connection vector field, and that gives us a displacement. So the way we compute displacement on a torus is we fake the area and subtract out. We get a displacement from the area integral, with that faking approach, and then we subtract out what the path integral in the connection vector field is for these other two edges. This thing we pre-compute in advance. So our belief is, since you can pre-compute in advance, who cares? And then off we go. So that's how we deal with the torus or cylinder or beyond that. Now, when you say non-Euclidean manifolds, I don't want to promise every I'm just going to promise
The vector of a manifold.
well, that's all robotics don't really care about. It's spheres, toruses, and cylinders, and multiples of them.
Okay.
And then the last question about the efficiency, that's a longer conversation. Airplanes have jet engines; they don't flap their wings, but we're optimizing different things at that point. So I think we're the phrase is apples and oranges. I think we're comparing different things at that point as to why. But it's worth noting, if you have a differential drive car, the connection's different. But if you break the wheel so they can't spin all the way, then all of a sudden this stuff is useful again. So the question back, yeah.
So you talked about
Mhm. So the needle insertion system is a straightforward compliant controller. We want to apply a force and we keep going. Yeah. So the mechanism. What's cool about the mechanism is there's a way of inferring force when being pushed in. I just don't think that's a big deal. I'm more impressed with the ultrasound close. That's why I talked about that. I thank you. Yeah, my engineer just made it work.
I'm talking about the geometric gates again. Based on non-autonomic constraints, is there any meaning to the rate at which different parts of the gate are traveled through?
So the short answer,
yeah, constant omega.
Right. So the answer is no. So that's the beauty of the method. In other words, we're taking things that are time-paced and making it all geometric. So if you go twice as fast around the gate, you'll go twice as far.
Yeah, I'm talking about different speeds along the gate, like different regions of the gate. Go slow for this part where you don't have like large constraint, and when you do manage to get a nice constraint of the non-autonomic from the shape of the robot, try to get a lot of effort done by this constraint.
Yes, so I think we're having a little bit of a communication thing issue. So the constraint is always there, okay? So Ross has developed these optimization techniques that do optimize whatever measure of energy you want, that essentially it's the volume divided by the path length you go around is essentially it. But it doesn't specifically say go faster here or slower here. I think did Shai do something? Did Shai Revson do something where he regulates the speed of the gate as he goes around? I don't think so, but I think the reason why the answer is no so far is because everything here is geometric, and that was something we were happy with. There's no dynamics, and so that begs the question: why do everything geometric? And the reason is, we do things geometric because it's easier. That's my thing. But the truth is, understanding geometry, I think, is the necessary first step. You know, if you look at any dynamic systems, the first thing they do is kinematically model things, and that's where we're at here. But I think what you're asking is, as you go around a gate, you get your configuration may get closer or farther away from, say, a singularity. I think is what you're asking, and yeah, you could regulate the speed there. I don't know what you get out of it, or at least that method won't tell you anything measurable you get out of it.
Okay, maybe you have one last question.
So I had a question about your robot impedance controller as well. You said above a certain obstacle size, you need to include plan A. Is that just a scaling effect of the size of the robot, or is that due to the dimensionality of your?
Oh,
you said you reduced the dimensionality
I'm
of your
sorry.
impedance controller.
That was not what I said. There was a non-rigorous statement.
Okay.
I was acknowledging after a certain point things don't work. But you are right. I should know. Is there?
Is it due to the scaling of the
Yeah,
size
yeah.
of the robot relative to the obstacle?
Yes, and that's the intuition. But that's just me saying, yeah, you know, the objects are this big, we're good. If it's this big, bad. And
But you're also doing a two-dimensional impedance controller, right? So could you do something in three dimensions?
it's a three-dimensional impedance. Yeah.
Oh, I thought you said-
No, I lied. What happens is there's two waves going through the robot. There's this lateral wave and a vertical wave, and we're doing impedance control in both of them. Yeah,
Great. So we're right on time. Thank you again, Howie.
I think